Hello, everyone. So today we're going to continue our conversation on kinetics by focusing in on one of the most common and most well-studied types of reaction mechanisms. That's enzymatic kinetics. But before we do so, I want to take a brief moment to pay some acknowledgments to Maud Menton, who is one of the pioneers who helped describe the behavior of enzymatic kinetics and lend her name to the famous Michaelis-Menten model. So whenever you're talking about Michaelis-Menten, always make sure to pay a little bit of attention to one of the uh, pioneers and one of the most foremost female biochemists, Maud Menton. So with that as uh, with that said, I want to go ahead and focus in on the reaction mechanism that she was so famous for studying. So when we're looking at enzymatic catalysis, they often occur via two discrete steps. So we tend to have an enzyme and a substrate, which then combine to form an enzymatic complex, which here we're going to represent as ES. And then the reaction can proceed to generate a product and release the enzyme. But one of the important things, part of this mechanism, is the fact that once the enzymatic complex forms, it doesn't always have to proceed to completion. It can often go backwards in a pre-equilibrated fashion to regenerate the precursor enzyme and substrate. So you may note that this is essentially a modified form of the pre-equilibrated mechanism that we talked about last time. However, there are some special features of this mechanism that do render it quite unique. So the first thing that we might notice is that we're going to care about the generation of product in this reaction mechanism. And so, not too surprisingly, this is going to be given by the rate constant for the second enzyme catalyzed step times the concentration of this active enzymatic complex. However, that brings us to, of course, the problem of trying to determine the amount of enzymatic complex present. So here we're going to end up making use of the steady state approximation. And this is actually fairly robust in the fact that the enzymatic complex forms relatively rapidly, but can just as readily decompose, and that we're going to see this uh, the forward reaction of the enzymatic complex, this second state as typically being rate limiting, because this part is often diffusion limited, whereas this second part um, is going to take a fairly significant energy barrier to overcome. So using the fact that the steady state approximation will be fairly robust in this model, we can essentially uh, generate a form for the change of the enzymatic complex as our once possible route to production, being the forward reaction, which is dependent upon the forward reaction constant and the concentration of both the enzyme and the substrate. However, this enzymatic complex can decompose in two methods, either the forward reaction, which we're hoping for, or the reverse reaction, which can still proceed fairly readily with a rate constant of K1 prime. From here, because we have steady state, are able to make use of the steady state approximation, the concentration of this enzymatic complex can be given by the ratio of our equilibrium constants times the concentration of our enzyme and substrate. Now, because K1, K2, and K1 prime are going to be inherent to the individual enzyme being examined, we're going to essentially combine these three rate constants into a single constant, which we're going to call the Michaelis constant. And again, if you note from here, the units should be of moles per liter. And you can see this as we have essentially concentration squared in our reactants and a concentration units in our products. So again, to keep our units balanced, the Michaelis constant should have units of, again, moles per liter, or possibly other metrics depending on what form of concentrations we're examining the system in. So with that put aside, we need to we can complete our analysis by making the approximation that the free enzyme concentration, the free enzyme is going to be dictated by the initial enzyme concentration minus any amount of enzyme that's essentially caught up in the enzymatic complex. Because again, any enzyme is either going, as soon as it forms the enzymatic complex, will then decompose to make the free enzyme. So we can give this our enzymatic concentration as a function of our initial concentration, which I can measure, and the enzymatic complex, which is exactly what I'm caring about. So I can insert this expression into my expression for the enzymatic complex, and then we can essentially distribute out our function. And so we'll now have the enzymatic complex as a function of the substrate times the enzymatic complex times the substrate. So what we're going to want to do is move this second term over to the left-hand side. So I have all of my terms for the enzymatic concentration, the enzymatic substrate together, which unfortunately does give us a little bit of a messy precursor, one from the original enzymatic substrate, and this plus the substrate concentration over the Michaelis constant, essentially coming from this right-hand side, leaving behind a term based on the initial concentration of the enzyme, the substrate concentration, the Michaelis constant over here on the right-hand side. So we can then divide both sides by 1 plus the substrate constant over the Michaelis constant. Now I'm going to essentially, to help simplify our expression, do this as multiplying it by 1 over this value. So from here, what we can do is spot that I'm going to be left with the initial enzyme concentration in the numerator. And for the denominator, well, here, my Michaelis constant and the substrate constant will cancel out in the second term and essentially switch inverse for this other term. So what I'm left behind with is the concentration of my enzymatic complex as a function of the initial enzyme concentration, the Michaelis constant, and the amount of substrate I fed into the system. However, we're often going to be interested in limiting scenarios. So one of the easiest approaches I can make is that since our substrate concentration is so much larger than my enzymatic concentration, that for most relatively short kinetics runs, so unless I have a very active enzyme, what I'm going to tend to see is that my concentration of substrate is going to remain relatively unreacted and relatively fixed. So I can replace my substrate concentration with my initial substrate concentration. Now, this may seem a little bit arbitrary, but the issue is that I might not always be sure of how much substrate is present in the system at any given time, unless, say, it's photoactive. But my initial concentration is well dictated by the solution I prepped. So I can usually determine what my initial concentration is. So this, again, lets us determine the concentration of our enzymatic complex based on 3 quickly measurable properties. Also, it shows that the enzymatic complex is going to essentially follow several rules that we would expect. Is that I'm going to have a large amount of this catalytically active complex when I have a lot of enzyme, or a lot of my substrate, or a very low Michaelis constant. Now, this seems a little bit weird because we think of this K as indicating the rate of reaction. So we'd expect this guy to be high for fast reaction. But we want to take a look at what the Michaelis constant is actually telling us. It's more or less the ratio of the degradation of the enzymatic complex, either to form product or to regenerate my substrate, over the formation of the complex. So while a large K2 is going to generate a high catalytic rate, we also are building in the fact that a large K1 prime is going to essentially draw down my enzymatic complex. And either way, both of these values will dictate a low enzymatic complex, formation of the enzymatic complex. While a large initial rate constant, this K1, is going to dictate the quick and rapid formation of a lot of complex. So this helps drive forward a lot of the trends of the Michaelis constant. But this brings us to the question of, well, why was I trying to determine the concentration of the enzymatic complex again? And for that, we need a quick reminder that the rate of reaction, or in this case, the generation of my product, is going to be given as the rate constant for the second step of the reaction. So this is the actual catalytic step times the concentration of my enzymatic complex. So we can then insert our equation for the enzymatic complex and derive an overall equation for the rate of reaction, where in this case, our rate of reaction for a catalytic mechanism tends to be given as K2 times the original enzyme concentration over 1 plus the Michaelis constant divided by the initial amount of substrate present. So let's go ahead and look, and this generates essentially a behavior seen here at the right. Low substrate concentration, low rate of reaction. As I increase the substrate concentration, I see initially a fairly rapid increase, but eventually, as this value just gets larger and larger, I drive this value to be near zero, and so this one factor dominates. And there's a certain value that I essentially can't get my rate of reaction past. So let's go ahead and take a look at this behavior by looking at these limiting circumstances. So first, if I have a very low substrate concentration, so this is again where my substrate concentration is much lower than my Michaelis constant. Well, in this case, what I find is that this one value is going to be relatively ignorable, and I'm given a value of Km over the substrate concentration. So the substrate concentration essentially becomes equivalent to being on the numerator. So I'll find the rate is going to increase as a function of the catalytic rate of the reaction. I'm going to see an increased rate of reaction with increased enzyme concentration, and as we see here, a linear dependence upon the substrate. So I'm going to see a linear dependence under this low concentration condition in between the amount of substrate I feed in the reaction and the rate of the reaction. Now, what you'll notice is that this doesn't stay true forever. And as my substrate concentration gets much larger than Km, well, at this point, this whole term essentially drops down to zero. And then all I'm left with is 1 here in the denominator. So my rate becomes equal to K2 times the enzyme concentration. And this rate, as you notice, can't be exceeded. And so this is thus called the maximum rate, or more colloquially as B max. So we can also make use of this expression of V max to help simplify my description of the rate. So we can replace K2 times E naught as just V max. So I can give my rate as the maximum rate that this enzyme can accomplish divided by 1 plus the Michaelis constant times the initial amount of substrate. So because we love to make these systems rather simple to graph and extrapolate, we can essentially linearize this equation as 1 over V is equal to 1 over V max plus the Michaelis constant over V max plus 1 over the substrate concentration. And the reason why this is so nice is it's fairly easy to control the substrate concentration and then measure how the the rate of reaction changes as a function of that substrate. So what we can do is plot this inverse of rate against the inverse of initial substrate. And what we can then do is come up with what's called a Lineweaver-Burk plot. So with this linearized form, what we find is the slope is going to give me information as to the Michaelis constant and V max. But more importantly, this intercept gives me 1 over V max. It gives me the maximum rate of this reaction. And the reason why this is so beautiful is that once I have this maximum rate, if I know the enzymatic, if I know the enzyme concentration, I can use that to back calculate my K2. And I can also use this Vmax to help give me my Michaelis constant from the slope. Because as soon as I know my Vmax, I know my slope, I know my Michaelis constant. And using the Michaelis constant, then we can essentially extrapolate out a ratio of K1 to K1 prime and figure out more or less the equilibrium of the formation of that enzymatic complex. So this is quite a potent way to simply describe the enzymatic behavior of many enzymatic catalysts. So we love getting this mechanistic behavior out of these biological systems. And so as a consequence, you'll often see Michaelis-Menten kinetics show up in a great deal of circumstances. However, it is worth noting that many non-enzymatic catalysts also follow very similar behavior. So don't be too surprised if you'll see Michaelis-Menten kinetics in other non-enzymatic systems. It usually just indicates the presence of a catalyst. But that doesn't mean we can't steal from the biochemist and use Michaelis-Menten kinetics and Lineweaver-Burk plots, as they are incredibly useful. So next time, we're going to spend some time playing around with other complex kinetic systems. Until then, take care.